Capacitors in circuits. We've discussed the theory of a capacitor at great length. Now we're going to see how it behaves as a circuit element. So we have a simple circuit here. We have a battery. We have a switch that can be connected to either point A or point B. We have a capacitor. There's a voltage difference here. There's a potential for the battery. And here's a light bulb. The capacitor has no charge on it. It is electrically neutral, no potential difference. The light bulb is not lit. No current is flowing. We now close the switch to position A. We have a complete circuit, and electrons from the capacitor's top plate are attracted by the positive terminal of the battery. The charges move through the battery, they gain energy, and are deposited on the bottom plate of the capacitor. Recall, conventional current is in the opposite direction of the electron flow. It's the direction of positive charge. So conventional current would be going this way. And what do you notice here on the capacitor? We now have signs on it, right? As electrons leave, this is positively charged. As electrons come over here, that gets a net negative charge. However, when you sum these two charges, you get zero due to the conservation of charge. They are equally and oppositely charged. Again, as the electrons are leaving the top plate of this capacitor, leaves behind a positive charge, they go over to the other plate, a negative charge, and these are equal in magnitude. The question, what happens to the brightness of this light bulb? And brightness depends on how much current is flowing through the light bulb. When the switch is closed, the maximum amount of current is flowing and the light bulb will be at its brightest. That's because there is no potential difference at the capacitor, so it is not opposing this potential. As the plates charge, the potential energy here, the potential difference increases, and as you can see, it opposes the potential difference from the battery. A way to look at that, this will generate a current going in this direction. The capacitor would generate an opposing current. Therefore, the net current in the circuit starts decreasing and will eventually be zero when the magnitude of the two potentials here are the same. Therefore, the light bulb will get dimmer and dimmer until the current stops and the light bulb goes out. The charge on each one of these plates now is at its maximum. We now have a fully charged capacitor, and it is charged to a potential that equals the potential of the battery, but in the opposite direction. We now move the switch from position A to position B, which takes the battery out of the circuit. Electrons will start flowing now, but this time in a clockwise direction, because conventional current leaves the positive side and goes this way, which means the electrons will flow in the opposite direction. So we have a current here that does not involve a battery. The current is being supplied by the fully charged capacitor. The potential difference across the plates of the capacitor decreases as the capacitor is discharged. This is unlike a battery. A battery maintains its electric potential by chemical reactions changing chemical energy into electrical energy. Capacitor doesn't have that. As the charges flow, the potential is decreasing. So what is going to happen to the light bulb now? As the potential energy decreases to zero, the current also decreases. Ohm's law, right? I is V over R, until no current flows. The capacitor is now fully discharged, and note, there's no more charge on the capacitors. Both plates are neutral. The light bulb, therefore, will get dimmer and then will turn off. The resistance of the light bulb also decreases as it cools off, but it still has a finite value. So when V is equal to 0, then I is equal to 0. Circuits with multiple capacitors can be redrawn as if there were only a single capacitor and a battery, just like we've already done with circuits with resistors. By reducing the circuit this way, the circuit becomes easier to study. We call this process finding the equivalent capacitance for capacitors in series, which is C sub S, and parallel, C sub P. We'll start with the circuit with just two capacitors. Let's use our prior knowledge. And what is the voltage across each capacitor? And what is the charge on each capacitor? The voltage across each capacitor is the same because they're in parallel. So we can say that V1 is equal to V2, and once you have two quantities with subscripts equal to each other, you can just replace it with the V. The total charge will be the sum of the charge on both capacitors here. So that would be Q is equal to Q1 plus Q2. And again, we're just going to use the charge on one plate here because we know that each capacitor is neutral, but we'll take the charge here plus the charge here. We'll use what we found on the previous slide where the voltages are the same and where the total charge is the charge on each capacitor, and then we'll use our definition of capacitance, which was C is equal to Q over V. So we start right here, this equation here, we replace each Q with CV. So we have CV is C1V1 plus C2V2. But what do we know about V1 and V2? They're equal to V. So we now have CV equals C1V plus C2V. Everybody has a V, cancel it out, and we find the equivalent capacitance for capacitors in parallel is you just add each individual capacitance. And if you have more than two, it's the sum of all the individual capacitances. The sum of the voltage drops across each of the capacitors in a series circuit equals the voltage of the battery. It's kind of like Kirchhoff's law, as a matter of fact. You start with a V here, and then you transfer some energy into the capacitor here, some energy here, and when you're all done, you come back with zero on this side, zero potential. So V is going to equal V1 plus V2. When you're in equilibrium, after these are fully charged, let's see, this will have a minus Q charge here. This will have a plus Q on this side. Since no charges are flowing, you have to have the same amount of charge here as here. So this also will be negative Q. If this were anything else, you would have charges flowing between the two of them. They have to be equal because this wire is neutral. There's no more current flowing. That would put a Q over here. That means the charge on each capacitor is the same. So we can replace Q1 and Q2 with just Q. We now have three equations to work with. The sum of the voltage drops across the capacitors is equal to V. Each charge on each capacitor is the same. And then here's your definition of capacitance, again in a slightly different format. So we will start with this equation here and substitute in for V, Q over C. So we have Q over C is Q1 over C1 plus Q2 over C2. We know that all the Q's are the same. So we can now have Q over C equals Q over C1 plus Q over C2. We can cancel the Q's because they're all the same Q. And we're left with 1 over C is equal to 1 over C1 plus 1 over C2. And if you have more than two capacitors, this is the more general equation. Relating this to resistors, we find that the equivalent capacitance is like finding the equivalent resistance, but it's reversed. Capacitors in series are added like resistors in parallel. And again, the caution, when you solve for capacitors in series, when you do the math on the right side, that doesn't give you the answer for the equivalent capacitance. What do you have to do? You have to flip that. You're finding 1 over C sub S. You want C sub S. So do the work over here and then flip the answer so you can get the capacitance in series. In parallel, capacitors in parallel are added like resistors in series. What is the equivalent capacitance if C1 is 12 microfarads and C2 is 18 microfarads? We write our givens, and this time, since we know the equivalent capacitance is going to be in microfarads, we're not going to convert to farads. We use the equation for capacitors in parallel, and all you do is add up each one of them arithmetically. So, CP parallel equals C1 plus C2. We have 12 microfarads plus 18 microfarads, so the equivalent capacitance for this parallel circuit is 30 microfarads. What is the equivalent capacitance if C1 is 12 microfarads and C2 is 18 microfarads? This time we have capacitors in series, since if the current flows this way, which it is, conventional current, it goes through C1. It has no choice but to go through C2 also. So that means it's in series. So here's the equation this time. 1 over capacitance in series, that's the S there, equals the sum of 1 over CI, where I is 1, 2, 3, etc. In this case, we just have 2 capacitors. So 1 over CS is 1 over C1 plus 1 over C2. We plug in the numbers here, 1 over 12 plus 1 over 18. And when you add them, make sure you flip the answer at the end, because when you just add these together, that gives you the value of 1 over CS. So when you flip it, you get CS is 7.2 microfarads.